Okay, we're being recorded now. So this Zoom session is being recorded. It'll be posted on our WAMAP course page, also on my YouTube account, Math Care for Your Brain Can Do Math. If you don't wish for your picture or name to be seen by others, you may shut off your video and use an alias name. Okay, so welcome everybody. Welcome Celeste and Juan and Yvonne. We're going to talk about linear growth, exponential growth, and logarithmic logistic growth. Now, linear growth, you all have studied before. It's when something grows at a constant rate and it makes straight lines when you graph it. So I'm pretty sure you've all seen, can you see that okay, everybody? Is that big enough?
Yeah, it's good.
All right, thank you, Celeste. So I know you're all familiar with y equals mx plus b. That's something that you've had, whether no matter what algebra class you took, you saw y equals mx plus b, where y is the vertical the variable on the vertical axis, x is the variable on the horizontal axis, m represents the slope, right? M is the slope, and b is the y-intercept. Okay. Now, we are going to use those same ideas where y is like it's called the output. It's the vertical value if you're graphing something. X is called the input. M is the slope again. That's the rate of change. That's a constant in any line. And if you remember, if you had a slope of positive slope meant the line would go up from left to right, and negative went down from left to right. So that's increasing if m is positive and decreasing if m is negative. And b is the y-intercept, which is the starting point when we did applications. So that's just kind of a quick review of that. Now I want you to see that we're going to use the same ideas, vertical or outputs, inputs, slope or rate of change, and a starting point b. But instead of b, we're gonna now use new notation, because different notation is used in lots of areas. So to get familiar with it, instead of y, we're going to use p with a subscript of n. In fact, I'm going to go back here. Do some of you remember? You probably remember this: f of x equals mx plus b. How many people remember that, where you had f of x with f and then was kind of the name of a function? How many of you have seen that?
I have seen this.
Yeah. Juan, Jairo, Celeste.
Yes, I seen it before.
Have you all seen that? Is that new to anybody?
That's new to me.
Okay, who said that?
Yvonne.
Okay, Yvonne. Okay, so this is called function notation. And this is where you'd put a number in for x, like if you wanted to have f of 3, and let's say that you had, I'll back up. Let's say you had f of x equals 2 or 2x plus 5, right? If you wanted to graph that, you could use 5 as the y-intercept, and then the slope of 2, or 2, you go up 2 and over 1. Do you guys remember graphing that? And then that way, but let's say you wanted to find a value. We would say f of 3 would then be 2 times, you'd have 2 times 3. You'd put the 3 in there. Whatever's here, that's what you plug into the function value. So that's what the notation implies. Is this x, this doesn't mean f times x. Just like this p is like a vertical value. If we were going to draw a graph, this would be the vertical value, and d would be the slope or the rate of change. In the applications we'll look at, instead of using the word slope, we'll call it constant difference. So here we call m the slope, we call d the constant difference. And x is the input variable, just like here, n is the input variable. B is like the starting point on the y-axis, and p sub 0 is the same way. P with this, I say P sub 0 because this is a subscript. The term sub means below, like a submarine or sub-level or whatever, it means below. So a subscript is something written below the rest of the stuff. Like an exponent, its general name is a superscript. So exponents are superscript. This just means P sub 0 means the starting point when n is 0. See, when n over here, when n is 0, that's the P value. So that's the instead of a y-intercept, we'll just call it a starting point. So here the starting point is 5. The constant difference we said was 2 earlier. So we could have that. That could be the same. So that's P with a subscript of n would look like that. This is like y equals mx plus b, but it's P sub n equal, oh, we would call that n then, wouldn't we? If this is an n here, that's an n, just like the f of x. Okay, hey, welcome, Raul. So that's just kind of the linear, this is the terminology. Now, these are called explicit formulas. You're gonna wanna, your notes for this quiz, for the quiz on, actually I'm gonna move the quiz to next Sunday. The notes for this quiz, you'll wanna write the explicit formula. And you could write these next to each other. You could write all this down. The recursive, and I'll talk about a recursive formula and what that means. Notice that this D occurs here also, but you're adding it. Now this P sub n and P sub n minus 1 is a tricky little set of subscripts, and we'll talk about, I'm going to talk about that in just a minute. Let me get open board open for you. I'm opening so I'm going to take this. I'm going to show you with that. Oh, that didn't translate very well, did it? That's interesting. I'm going to undo that. I'll go back. I'm going to take a screenshot of that instead. Yeah, that's interesting. Okay. So I'll take a screenshot of it. And now, let me go to this. That's better. Okay. So when you do a graph of a line, oh, let's just do a background. Let's make it a graph. So let's say we have y equals, well, that didn't work. Okay. Y equals 2x plus 5. Okay, so if we have a graph over here, y equals 2x plus 5, let's just review this real quick. If 5 is the y-intercept, I can go 1, 2, 3, 4, 5. I'll just put a dot right. Change this to red pen. And I go up to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's the red dot for 2, or for 5 is the y-intercept, right?
We
I can't see the screen.
Yeah.
Okay, thank you. I know why. Okay, I can redo this then. Let me, I'm going to stop my share screen. Let me do. Okay. Can you see it now?
Yep.
Everybody can see it?
Yeah.
Okay,
Yes.
so if y equals 2x plus 5, then 5's the y-intercept, right? And then the slope of 2 means you go up to 1, 2, and over 1, remember? And then you could go up 2 and over 1 again, because the slope is something that stays consistent throughout a line. And then we could draw that line. So I could take a point here and, oh, what happened? That was, that isn't what it's supposed to be. I was clicking on the straight line. So it should make it perfectly. So there we go. So I could draw that line like that right through those points. And then, you know, I'd go ahead and put arrows on the end to show that that's going to keep going on to infinity, right? That's how we draw that line. Well, the same thing is if I had the function p sub n is equal to 2n plus 5. That means, now typically we don't draw lines for these. We don't graph this when it's got subscripts of n, because we usually think of n as whole numbers. So we might make a table with n here and p sub n here. So with the types of functions we're talking about, we're making tables. So n, if n starts out at 0, p sub n is 5. And then if n goes on and, you know, then n is 1, what's going to happen? If n is 1, we get 2 times 1 plus 5 is 7. If n is 2, we get 9. If n is 3, we get 11. And you can see this is something when I first teach linear functions to students, I always want them to look and notice something. If this goes up consistently, like by ones, notice that this should go up by 2 every time. 2, then 2, then 2. Okay? That's what linear growth is. Okay? Linear growth, oops. Okay. So linear growth means this is going to be a constant. This is a constant difference. And notice the constant difference, isn't it in the place of the slope, right? It's just like the slope. So if I gave you a set of values and I said, here's n and here's p sub n, and I said, when n is 0, p sub n is, let's say, -8. And when n is 1, p sub n is -4. And when n is 2, it's 0. And when it's 3, it's 4. And when it's 4, it's 8. And when it's 5, it's 12. What is the obvious pattern here? On the left, they're always going up by 1, right? And on the right, what's happening every time?
It goes up by 4.
That's by 4.
Yeah. So we see here, I'm going to call that D. This is going by 4, by 4. I'll put a plus there because we're adding 4, right? That is what makes this function linear, really, is that it has a constant difference, which would be the slope, right? If you checked out, remember the slope formula? You take y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And you should be able to do that with any pair. Like let's go from 5, 12, and 0, 8. So it would be 12 minus -8, right, in the y's, the output. And 5 minus 0 would be the difference in the inputs. And 12 minus -8 is 20. And 5 minus 0 is 5. And 20 divided by 5 is 4. So we get the slope. Well, we can see that just by looking at a pattern if we have that series of numbers, right? That sequence. So you can see D. Now, how would we write this equation? We would say this equation is P sub n, like y, is equal to mx plus b. But what's our m? Our m is 4 in this case. Instead of x, we'll use n. And instead of b, what's the value for b? It's, remember, b is the starting point. That's -8, isn't it? So I'm going to erase my plus sign and put -8. That is the explicit function. So that's called explicit. Y equals mx plus b, or p sub n equals d times n plus P sub 0. It's the same as Y equals MX plus B. Okay? So why are we doing all this notation? Because we, in your original math classes, we focus on explicit formulas like this. They're really nice. Explicit formulas are great. You can find, if I want to find y, let's say right here, y, let's use this one, y equals 2x plus 5. If I want to find y when x is 30, what do? I just put a 30 in. 2 times 30 for x, right? 2 times 30 is 60, and 60 plus 5 is 65. So I know the ordered pair here is if I get 30 for x, I get a 65 for y. Similarly, in this function, it'd be the same thing. Or in this one, we see this pattern. Let me do some erasing here. I'm going to get rid of the 2x plus 5 part now. All that. Okay. Now, if we just had this pattern, the -8, -4, 0, 4, 8, 12, you can tell what that pattern is as you keep going, right? What's the next number going to be?
14?
We're going up by how much?
I'm
16.
sorry, 16, sorry.
16, you mean, yeah. I knew you meant that. And the next one is going to be 20. Now, what's the 100th term going to be? This is term, well, if we call this term 0, then the first term, we'll call this the first term. If this is the first term after the starting point, and this is the second, how far to get to 100? Well, we would say,
Wouldn't it be 92? You just do 400 because it would go up, and then you subtract the initial.
yeah, P sub 100, I should say. What is P sub 100? Yeah, it's going to get 4 times 100 minus 8. Isn't that what you were saying?
Yeah.
Multiply it by 4 and then subtract 8. So that's what an explicit formula does. 4 times 100 is 400. 400 minus 8 is 392. So you can find the 100th term super easy, right? Also, if I said which term has a value of 4,164, right? Then you could put 4,000, 4,000, wow, I'm really messing that up. You could put 4,164 into that explicit formula, wherever it was up here, is equal to 4n minus 8. And you can solve for n, right? You remember doing this stuff back in first year algebra? You'd add 8 to both sides. And you get 4n is equal to 4,172. Then you divide both sides, by 4, right? So this is the wonderful thing about explicit formulas, is you can put big numbers in and find out what would happen way down the list without having to go one number at a time. And 4 goes in there, 1,403. So that would be n, that would be the 1,000, that would be P sub 1,043 would be the term. It'd be the 1,043rd term, or n would be 1,043. Does that make sense to everybody? What do you think?
Yes.
So that's the nice thing about explicit. That's what an explicit formula provides for you. However, one thing an explicit formula doesn't do for you is it doesn't generate a list. It doesn't generate a long list of numbers. See? If you wanted a whole bunch of these numbers, then the recursive formula is the better formula. And the recursive formula is kind of the pattern. It just observes the simple pattern. So when you say recursive, by the way, recursive means it's recurring. It recurs one step at a time. So what we were doing here, we're using a recursive notion, a recursive idea. What are we going to do for the next number? After 20, what are we going to do? Add 4, right? Then the next term, add another 4, add another 4, add another 4. Do you see adding 4 recursively? If you're adding 4 recursively, it generates the list. The list of terms. Well, we don't always really want a long list of terms, so we don't really always want a recursive formula. But let me show you what that recursive formula would be. Since we already had it, y was equal to 4x minus 8, and I said that's p sub n is 4n minus 8. These are the exclusive formulas, explicit, sorry. Okay. But a recursive formula would look like this. Those are explicit. They look like this. P sub n is equal to P sub n minus 1 plus 4. That's all it is. The recursive formula, it doesn't tell you, it doesn't have the starting value. What it has is the number that you do to a previous one. So this is important. This is what you add to the previous term to get the next term. So P sub, in other words, if you want to find P sub 8, if n is 8, what's the subscript going to be? Oops. If n is 8, what's the subscript going to be for this P sub n minus 1? It will be a P sub 7 plus 4. So what does the recursive formula tell us? It tells us if you want to find P sub 20, you have to look at P sub what?
19.
19, and then do what to P sub 19? You have to add 4 to it. Does that make sense?
Yes.
So in other words, a recursive formula doesn't tell you how to jump to like the 100th term or the 90th or the 1000th term or anything. It tells you how to get from one term to the next. That's all it does. That's all a recursive formula tells you is how to go from one step to the next, next to the next, to the next, to the next, to the next, and you do the same thing over and over. So this recursive formula, so I'm going to write this all with your P's. The explicit form is P sub n is equal to 4n minus 8, and the recursive form is P sub n is equal to P sub n minus 1 plus 4. All this P sub n, and this one thing I want you to learn from this today, important factor is that recursive formulas to find P sub n, that means any term, you look at the previous term, okay? So this is any term. That's what P sub n means. And this is the previous term. And this is, it's not really nice of mathematicians to do this. Now you've got new vocabulary. We've got this new subscripting going on. And mathematicians, by the way, did not develop mathematics thinking, how can we make this nice and convenient for students? They did not do it for you and me. They didn't do it. What to make this easy to teach? That's not why they did things. So they did things to communicate with each other. Mathematicians were primarily focused on communicating with one another. And that left us, when we learned it, and now as I teach it, to kind of scramble to say, well, what's the best way we can remember this? And so that's a little bit of the challenge of this particular material is we've got this kind of notation that's not really as convenient as it should be. But this is what we live with, okay? So we have explicit and recursive formulas. And mathematicians have reasons, and good reasons, really. There are good reasons for having those two different kinds of formulas. And you're going to see that recursive formulas are really nice in many ways. And I know you haven't done recursive, most of you probably have never seen recursive formulas before. So let's talk about exponential functions now, because you're doing linear. I don't think they're too hard. So I'm gonna get another page here. I think I'll change the background on this. So let's say we had a set of data and it said, okay, for 0, I'll make a table. We'll do n and p sub n. The starting point is, let's say, 8. And then the next value for 1 is going to be 12. And the next for 2 is going to be 18. And for 3, it's going to be 27. And then for 4, it's going to be 40.5. It's going to keep going like that. Now, does that look linear?
It does not.
Okay, and why? What is the problem? Why isn't that linear, Raul?
It's not the same number over and over again.
Okay, so here we added 4, right?
Yep.
And this we add 6, and this we add 9, and this we add what? 12.5. No. Oh, that should have been 41. Sorry, I made a mistake. That's supposed to be 41.5. No, that was right. It was 40.5. What am I doing? Yeah, that's right. This is 12.5. 13.5. I don't know what I'm thinking. It's 13.5. Okay, so this is clearly not linear. Okay? So I'm going to take and I'm going to erase those. Okay, it's not linear. And to get a linear function, we know really we're subtracting, aren't we? Right? We're subtracting to get that. 12 minus 8 and 18 minus 12. So we were subtracting those consecutive terms. But now, what if we divided those consecutive terms? What if we took 12 divided by 8 and 18 divided by 12 and 27 divided by 18? Instead of subtracting, instead of 12 minus 8 and 18 minus 12 and 27 minus 18, instead of subtracting, which gave us 4 and 6 and 9, since that wasn't consistent, let's divide. And what do we get when we divide? 1.5, 1.5, 1.5, and 40.5 divided by 27 is 1.5. So this was not a consistent difference. We called it a constant difference if we subtracted and got the same thing, if it was the same number every time. But this we call a constant ratio. And that is important too. That means it's exponential. So let's, okay. hang on just a second. So yeah, that's a constant ratio. And so I want to look at those. So I'm going to jump ahead to that, to exponential. So in exponential, we have this kind of these explicit formulas. So for the problem that we just were looking at, what is P sub 0 equal to? It's where n is 0.
8.
Yeah, so P sub 0 is equal to 8. This is what we call the starting point, right? And now we also have a constant ratio of 1.5. So as we look at this formula, P sub n, now I'll show you what we used to write as y and mx, y and b. P sub n equals P sub 0, b to the n power. B is our constant ratio. So, oops, why did I do that? Uh-oh, that was a mistake. Yeah. So, jump to the whiteboard. If P sub n is equal to P sub 0, b to the n power. Remember, this is like, you've probably seen this before, a b to the x. Do you remember that from math, your algebra class? A is the starting point, that's like P, B is still B, and X is now replaced with N. So P sub 0 is 8, so we get P sub N is equal to 8 times, and the constant ratio 1.5 is B, so it's 1.5 to the N power. And that's all there is to that. That's the explicit formula for that pattern that we just wrote right there. Okay? And I'm just going to write EX for explicit. Now, in implicit formula, not implicit, a recursive formula is P sub n equals B times P sub n minus 1. And I'll remind you that P sub n is just any term is equal to B. Now, what's B here in this case? B is 1.5, and P sub n just means the term before, the previous term. So any term can be found by taking 1.5 times the previous term. So how would we find term number 5? We would take 4.5 and we go 40.5 and we go times 1.5, and that would give us our next term. So 40.5 times 1.5, this doesn't turn out as nice, is 60.75. To find the next term, I could just hit times 1.5 again, and that's 91.125. I just keep multiplying by 1.5 and I get more and more terms. Okay, that's how exponential, now this is an exponential function, that's how exponentials work, is we multiply. See, this is a multiplication here. We multiply, we're multiplying by that term, okay, instead of adding, which is linear. Okay, so now I want to look at an application here. It says you collect data. You know, I'm supposed to check something. Hang on just a second, I'll be right back. Sorry about that. Sorry about that. I thought something was smelled in the oven. It's okay. You collect data and note that a fruit fly population grows from 40 to 100 in a matter of 3 days. It says, use the assumption that the fruit fly population grows exponentially and find both an explicit and a recursive formula that will model the population based on the given data, or on the data given. So it grows from 40 to 100 in a matter of 3 days. So I'm going to write that down on, I'm going to write it this way, N and P sub N. It starts out at 40. Now that's where it starts, right? If it starts out at 40, we put a 0 for N and put 40 there. Okay. Does that make sense to everybody? I'll have you take a picture of this in just a minute when I get going a little further. Now it says in 3 days, so I'm going to put 1, 2, 3. 1 day later, we don't know what that grew to. 2 days, we don't know what it grew to. In 3 days, we don't know what it grew to. Well, 3 days, we do know it's 100. Does that make sense? So here's what you do. You can find B. Notice that if it's a constant ratio, if it's exponential, see, it says it's exponential. There's supposed to be a number B that you would multiply by. So now move this. Okay, you're supposed to be able to multiply these two blanks. Oops. These two blanks, I don't know, but weren't you supposed to multiply by B here, then by B here, and then by B here? Does that make sense? So in other words, 40 times B once times B again is supposed to add up, multiply up to 100. You have to multiply it once to get to 1, twice to get to 2, and 3 times. So you'd have to have B to the third power. 40 times B to the third power equals 100. That's what that would be if it was an exponential growth, because it's supposed to be a constant ratio. Constant. We also call it a constant factor, or a constant multiplier might be the better word, but in math they use ratio. And how would we solve for B? Divide both sides by 40. We get B cubed equals, now 100 over 40 is 2.5. And now, do you guys remember how to find the solve for B? Anybody remember what you're supposed to do to solve for B when you have
The
B?
cube root, right?
Yep, you take the cube root, exactly, Malin, thank you. So we're going to take the cube root of both sides. So we take the cube root of this and the cube root of 2.5. And just so you know, I'm going to show you how you can do this on your calculators. When we take the cube root, that's the same as the 1/3 power. So remember, the cube root of something is the same as that something to the 1/3 power. So I'm going to try and show you how to do that on your well, I'm going to do it on my calculator right here. I'm going to quit that. I'm going to clear it all. Okay, so I'm going to take, it was 2.5, and I'm going to raise it to the power, and I'm going to put parentheses around it. I don't actually need parentheses because mine stays up in the exponent, but then I hit 1/3. Some of you will have to have parentheses around the 1/3. So I'm putting them there. On my calculator, I don't need them, but many calculators do. So just to be on the safe side. So there's my answer, 1.3572. I don't want to write all that out. That's way too much to write out. So I could just round it off if it was an application to like 1.357 or 1.36 maybe. Okay, I'm going to do 357 here. It's approximately 1.357. So an explicit formula, remember the explicit formula, I'll write it up above. P sub n is equal to P sub 0 times B to the n power. So I just found B, right? And over here, remember, this tells me that, I'm going to point it over here. This tells me that P sub 0 equals 40. So I have my P sub 0 and I have my B, so I have my explicit formula. P sub n equals 40 times 1.357 to the n power, and that's my explicit formula. Okay. Now the recursive formula, I'll write that, I should write the explicit here. P sub n is equal to P sub 0 B to the n power. The recursive formula, all you have to do is take B and multiply it by the previous term. That's all you do. So I'm going to take P sub n. All you need is B, 1.357 times the previous term. Just you got to make a note of this. You might want to write, this is the previous term. Okay, and this is any term. And that's always the previous one. You might want to take a picture of that page. I am gonna, this is being recorded, but still, this is kind of a good snapshot. Okay, so let's look at what we might do with that. It says, use the formula to predict the fruit fly population, when the fruit fly population will reach 1,000. So what does n represent here? N must be, if n 3 days, and then we got a 3 there, the n represents days, doesn't it? And the 40 and the 100 represented the population. Okay, so P sub n is my population. So when I have that, if I want 1,000, P sub n equaling 40 times 1.357 to the n power. Just remember, P sub n is the population, and n is the number of days. Okay, so this happens in my house a lot in the summertime. Fruit fly populations grow very quickly. Okay, I like pears and peaches, and man, fruit flies do too. So I get a lot of fruit flies. Anyway, when will it reach 1,000? Well, this is a population we're asking for. So the 1,000 isn't the n, it's not the number of days, it's the P sub n. And so I'm going to remind you of how you solve for an exponent, which you may have forgotten. We use logarithms. So when we're done with this, you might want to take a picture or a snapshot of this page too. So what do we do to solve for a variable? We always undo what's being done to the variable, right? The n is what we want. But to undo it, I think of it as unwrapping a package. It's important, the order that we do it's important. You can't multiply 40 by 1.357. Can anyone tell me why?
You have to do the exponent first.
Yeah, the 1.357 is raised to the n, and you can't multiply before you do a power. So when we solve this, you can't multiply 40 by the 1.357. You divide by 40 first. So I think of it as starting on the outside. The 40 is the furthest from the n, so we divide by 40 first. Now 4 goes into 125 times. And now there's two methods that people use to solve using logarithms. One is you can use the definition of a logarithm. And I'll show you what that looks like. To use a logarithm now, I'll put a little asterisk up here. Now use logs, okay? And one way, method A, I'll call it, is you can write this as log. Now, since 1.357 is the base of the exponent, it becomes the base of the logarithm. And then we use what's called the change of base formula, where you can rewrite this as the log of 25 over the log of 1.357. Okay? The other way is to take the log of both sides, where you take the log of 25 is equal to the log of 1.357 to the n. And then there's a rule for logarithms that says the n can come out and be a multiplier if it's the power, if it's an exponent on that base, or on the argument of 1.357. And so now, since we can bring that n, since that n can come out, we can divide both sides by the log of 1.357, and we get the same thing. See, these are equal. This and this are going to be the same thing. So our answer is going to be by taking your calculator and plugging in the log of 25. So I'll do that now. You get the logarithm of 25. And on mine, since this is called a prompt, it gives me a parenthesis without me pushing it. I have to close that parenthesis. And then divide by the log of 1.357. And again, it prompts that parenthesis. It automatically puts it there, so I have to close it and then hit enter. And so that says 10.544. I'm just going to round that off to say n is approximately 10.5 days. That's how you use the explicit formula to find values like that. You might want to take a picture of that to just remind you. And remember, you can solve A or B. I'll write this in here. You can solve it either way. Make it green. Or you've got two options. Okay, now I want to introduce the last topic. You all had a chance to take a picture of that if you want.
Just a sec.
Okay. Got her?
Yep, got it. Thank you.
Okay. I'm kind of a big one on my lessons to always interrupt me. If you guys want to take a picture, say, please stop and take a picture so you can take a picture. I want you to get those in there. So here's the last one, is logistic growth. And this is an interesting kind of growth. Let me give you a picture of exponential. If you remember graphing exponential functions, they often start out kind of flat and then they go going steeper and steeper and steeper, right? Now it's also possible for exponential functions to come down and go like this. They go either way. This is called exponential growth, and this is called exponential decay, when something gets smaller. Like the prices of a car, that's exponential decay. Now, logistic growth looks like it starts out as exponential. I'll give you a picture of, well, you already know linear growth, but logistic growth looks like this. It starts out looking exponential, and then it curves back around and flattens out. That's logistic growth, okay? You might want to take a picture of that. It's also possible that in logistic growth, we get something like this because we overshoot and it goes too high and it kind of goes like this. You can get that kind of thing with logistic growth also, okay? Okay. Now I want you to see I don't know why that's in there. This is craziness. I don't know why that's there. Shouldn't be there. Yeah. Okay. So this is logistic growth. And notice it says recursive formula. In the other two formulas, we did not have we had both explicit and recursive. On this one, that's why we're teaching you recursive formulas, because on this one, we only get a recursive formula. So you have to be at least familiar with recursive to do logistic growth in this class. So here's the idea of logistic growth is populations usually can't just keep growing forever and ever and ever, right? I mean, Earth, it can only hold so many people. I mean, it might stack us up, but there's not gonna be enough food supply and water, and it just isn't gonna, well, there's lots of water, it's just not clean, but we can't drink it yet. But anyway, there's just, it's gonna curve off, it's gonna flatten out at some point. And that's true with most populations. If there's a limited space, then the population can only get so big. I mean, cougars, there just aren't going to get huge populations of cougars because cougars, they have huge territories and they'll kill one another. You know, they need a lot of space. So the populations for cougars is limited. And if there gets to be too many cougars, then they're going to start dying off because they will start killing each other, competing for food. They have territory and they'll defend it. Anyway, this is the formula. And P sub n, remember, P sub n stands for any term. And what's P sub n stand for? The term before, I'll just write PREV. The previous term goes there. Also, this is the previous term. And this is the previous term. So see, this formula is a little more complicated. All these, it has three, you have to use the previous term 3 times. So this is not a simple little recursive formula like the others. And notice I rewrote it here with, instead of P sub n, I said, if you want to find B, you have to look at A, which is the term before it, add a growth factor R, 1 minus A over, and K, by the way, is the maximum capacity, or called the carrying capacity of the area. But notice A turns up here, here, and here. That is, to find the value for B, you have to look at the previous term, add this to it. Now I gotta say, this looks a little bit like, this is a little bit like exponential growth, but this number right here, this is a 1 minus A over K. And if we had a normal class, I'd spend a whole class period talking about this. But we're going to spend a few more minutes. So let's talk about, okay, I'm going to erase these now. Okay. Okay, let's assume that a population of doves has a normal growth rate R of 65%. Now that's R, that's 65% right there. And we'll write that as 0.65. So, but a given area has a carrying capacity of only 5,000 doves. That is our K. And the dove population is already at 500. So that's our P sub 0. So to use the logistic growth recursive formula to find the population over the next 10 years. So I'm going to plug this in. Here's the formula. It tells us that R is equal to 65%, so that's 0.65. It tells us that K, that's the carrying capacity, is 5,000 doves, okay? $5,000. Now, P sub 0, this is year 0, which we don't have, that's 500. That's our starting value. We'll come back to it. So what do? To find the next value, to find P sub 1, we start out with the 500. We add 0.65, there's our R. And then we have 1 minus the 500 over 5,000 times the 500. So I guess I should change my color on my 500. I want to write that. That's 500 here, here, and here it's a new number each time. So I'm going to put that on the calculator. So I get 500. Oops, that's an extra 0. So 500 plus R is 0.65. Move that to the side so you can see that. And then parenthesis 1 minus 500 divided by 5,000. Oops, that's an extra 0 again. I gotta back up and delete it and close the parenthesis, and then times 500. Okay, and I'm gonna enter. That gives me 792.5. So that's my first one, is 792.5. And then how do I find year 2? Well, now I have to put the 792.5 in there. Here, here, and here is where I put 792. See, A, and A, every time the previous number. So that's going to be 792.5, that's going to be 792.5, and that's going to be 792.5. And all the other stuff, I'm going to go back to orange. That's going to be that plus 0.65, the 1 minus, that's going to be over 5,000. Those are going to be the same each time. So now what do I have to do? I can go back to my calculator and I can do it all over again. 792.5 plus 0.65 parenthesis 1 minus 792.5 close parenthesis. Oops, nope. I have to divide by, divided by 5,000. See how easy it is to make a mistake? And then 792.5 and hit enter. Okay, now, is there really going to be a half of a dove? Is it really going to be 792.5? It really can't be a half a dove. So I could have rounded that off to 793, right? 793 would have been a better thing to round it to. But now, what did I just find? I found that the next number was 1225.97. So I'm going to call that 1226. 1226. And now how am I going to find P sub 3? I'm going to have to put the 1226 there, there, and there in my formula. Right? The 0.65 and the 5,000, notice that the 65% and the 5,000 are the same each time. You always get 1 minus, so you always have the 0.65. The growth rate and the carrying capacity are always the same, but now the new number is 1292 or 1226. 1226, 1226, and 1226. Does that make sense to everybody?
Yes.
Okay, any questions on that? Now I'd have to redo that whole thing, but let me show you something. If you have a TI 85 or 6, you can just put 1226 in and hit enter. Once that number's in there, you do not, I'll show you what you do. You never have to enter 1226. I can go second answer and it thinks that's the 1226. Then I go plus, now 0.65 is the same every time, parenthesis 1 minus, and then I hit, instead of 1226, I go second answer. And then I divide by 5,000. Divide and then times by, instead of 1226, I put second answer. Notice where second answer shows up every time, right here, right? Answer, answer, answer. And now when I hit enter, it gives me the next number. And now here's the magic of the TI 84. We know that the third year is about 1828. So I can go over here and say that's about 1828. But now watch. If I take that number, if I take that calculator and I hit enter again. I don't have to push any other numbers. I just hit the enter button. And look what it does. It takes this answer, and notice, isn't this the exact same line as this line? But it gives me a different number because it takes the 827.5 and it puts it in here now. And I don't have to keep doing it over and over again. In fact, I could have started that way. So that gives me 2581. And I hit enter again, and it gives me that's the 5th year, then the 6th year, then the 7th year, and so on. So do you see how a recursive formula can be really convenient using a calculator like this, that you can just keep hitting enter and it'll do the same thing over and over again with the new number. It gives you the next term and the next term and the next term. So that's the wonder of the TI-84 and other calculators. There's some other calculator, any calculator that we can hit second answer and it'll record what you did, it'll do that on. Okay, so if you have a different calculator and you want to stick around and see, you can do that. And I'll just do this one more time for you. If I started out with just the 500 and I'd gone second answer plus the 0.65 parentheses 1 minus second answer divided by 5,000, all I need is that growth rate and that carrying capacity and a place to start. And I put my answer in there. I hit enter, and notice it gives us the 792.5 and the 1225, and you can just keep clicking and clicking and it just gives it to you over and over again. Does that make sense? So this is a really convenient way. Now, of course, notice I put the number in first all by itself and hit enter. So that's how you can use that. If anybody wants to stick around and go over how to do that more, I'd be happy to help you individually if you want to work on it and practice it. So that's how you do that for going from year to year to year. That year 4 is the 1827 and year, 1827 and 2581 and 3392, all those numbers we can fill in here. Oh, I already did the 1827. Yeah, 2581 is year 4. So, and then year 5 was the 3393. Oops, 3393, and so on. Okay, so that's the chapter in a nutshell. Hopefully that'll help you get a good grasp of what's going on in there. Anybody have any questions at this point? If you'd like to stick around and practice, I will be happy to stay after and do that. And you can try it, and if it works, great. If it doesn't, you can show me what you did and I can help you correct it. Because this tends to be the hardest stuff for people, is the recursive formulas for logistic growth.
Mr. Lewis, I have a question actually.
Go ahead,
When will this video, just for references, I think I asked this last time too, just in case I need to reference back to this video, when will it be available?
It's going to be available sooner this week than last week. Last week I had a pain trying to get it uploaded. I realized that I tried to upload it from Zoom and it just doesn't upload well from Zoom. I just ended up uploading it to my YouTube video. That's why before I just say I'm going to upload it onto our class, but I'm uploading it onto my YouTube channel, and then I can just load my YouTube channel in. So I'm going to do it right after class.
Perfect. Thank you for that information.
You bet. Anybody else? Anybody want to take, I kind of erased this. I probably shouldn't have. I didn't erase it, I just covered it. Anybody want to take a picture of that? Go for it.
Sure will.
Oops, I don't know what happened there. Let me know when you're done taking a picture of that. I'll put the calculator up there too, so you can see what if you want to take a picture of the calculator, what's written on the calculator too. Okay. Okay, I'm just getting a getting a text from one of your fellow students. Okay. Okay. Do you want me to put up the calculator now? You would want a picture?
Yes, please.
Okay. I'll go up a little higher to where I put the 500 in, so you'll see it kind of right from the binning. And this is important. See how the 500 is highlighted? You have to put 500. You have to put the first value in. Okay, that's the only time you type in the 500. Now the 0.65 and the 5,000, they're part of the formula. But remember, 500 is where you started. So you have to put that in and hit enter before you use the answer thing. But there you go. Okay. Any questions, anyone? Okay, I will go ahead and stop my screen share. And by the way, the writing assignment, I just posted the forum that you can post that to. I'm gonna talk about I'm gonna offer small group opportunities later in the week too. So we can discuss, prepare for the quiz a little bit. This is harder than the voting theory stuff. And by the way, people did great on voting theory. I mean, the papers, particularly the ideas on RCV, a lot of thoughtful input on those. People gave it a lot of good thought. It was great. You're a great class. Anyway, yeah, this next assignment is harder, and I usually it's common. Don't feel uncomfortable if I say, okay, here's where there's an error. I'm going to send it back. A lot of times I send it back and say, here's how you can improve your grade. If you don't get a real high grade, then I send it back and give you a chance to up it. So that's very common. A lot of people are tweaking and redoing some things on this writing assignment. So everybody wants to do it best the first time. It's nice, it's done, and it's over with. And no one likes to, hey, here, oh, could you redo this part of it? But don't be surprised if that happens, and that's okay. I just want you to have a chance to get a better grade. So, but also, I also would we all would prefer it if you could give your best shot on the first try. And on that paper, it's really quite a bit. You have to look at quite a bit of stuff. I have a video that shows you how I go through that process, but there's not everything is linear growth or exponential growth or decay. They're not all linear or exponential. And some people pick things that are not good examples of linear or good examples of exponential. And so you can pick either linear or exponential. So when you get data, you have to look at it and say, does this really look linear or does this really look exponential? And that's, and do a test, and we'll look at the numbers. We'll see, is there a pretty constant difference? Like we do all the subtraction, it doesn't have to be perfect, but if we'd have gotten 4 and then 3 and then 4 and 3.8 and 4.2 and 3.9 and 4.1, we would have said, now, 1 was a little off, but mostly they're really close to 4. So we'd say it looks like it's linear growth. Or on the exponential one, where notice it came out to be exactly 1.5 every single time, that was exactly an exponential growth. But you might have something like 1.072, 1.075, 1.069, 1.071, 1.067, 1.070. Well, those are all pretty close to about 1.7. So you'd say, we know it's not perfect, but it's really close to exponential. But you're going to be doing that when you look for data. And I give you some examples of what you can be looking up. And that's really something that you're interested in too. I don't want you trying to, if you have no interest in population growth, don't look for population growth. I did something on, my example has basketball salaries of rookie basketball players, the starting salary. I really like basketball, so I did that. Anyway, I'm also interested in the national debt. So I did one on the national debt, and the national debt was neither linear nor exponential, wasn't very good. So I ditched it. I said, well, I'm not going to do that one because the national debt changes for lots of different reasons. It's not very consistent. So anyway, I hope you feel free to contact me. I'll be here from 11 to 12 tomorrow. I'll be here from 11 to 12 on Thursday, also doing another review and also just answering questions on the assignments if anybody has questions there. So if there's nothing else, thanks for coming. Glad you all made it. We'll see you on Thursday, or if not before. Okay, take care.
Thank you.
Bye-bye. All right. How's it going?
So far, so good.
Okay. Anahi, she's here pretty regularly. That's great. Okay, well, I'm gonna take off and try and get my video uploaded as soon.
Okay.
Okay, thanks. Bye-bye, Panyada. Hope you had a good weekend.
Bye, Doug.
Bye. Oh, how was Sunday night?
Oh, I didn't send you
I don't-
report.
I didn't, you know what? I haven't checked my mail.
Did I send it?
I don't see anything. Nope, I don't see an email from
Okay,
you.
I will send it. I will send it. Okay,
Yeah,
thanks.
no problem.
I'm sorry.
Oh, I have an Anahi. Huh.
You what?
She's Math 93.
I know, she sent me an email.
Oh,
You know what it says?
what?
Hello, Professor Mayo. That was this morning. Oh, now it says, hello, Professor Lewis. I'm sorry I did not inform you I was in Mexico because my grandparents got sick. I'm very confused on how to use WAMAP. Oh, this is a different, no. Anahi Lamas. Oh, this is really interesting. Oh, she called me Mayo, but she's actually in my class. And her name is Anahi. I've never had an Anahi before. I've never heard anybody named Anahi before. And now there's an Anahi in Trevor's breakout room in Math 93, and there's an Anahi in my Math 107.
How funny.
Go figure. And she called me Mr. Mayo. Now that's confusing. I'm glad she wrote a follow-up. I don't remember seeing her name on my roster. That's the thing, but she's on in my class.
So was your meeting just now for your Math 107 or was it for something else?
It was for 107.
Oh. My daughter really should have she signed up for 107. She must not have signed up for you. She must be in somebody else's 107.
Yeah, either Kevin might have one.
Kent?
Kevin, no, oh, sorry, Kevin.
I don't know who she has for 107. She has somebody for 107.
How come I cannot think of Kevin's last name? Dyke, Kevin Dyke.
Yeah, I have no idea who it is.
Yeah.
I thought it was you. I told her to sign up for you. So
Yeah, Abby, I don't think she's in my class.
yeah,
Yeah.
that's where I told her to sign up for. So she must have signed up for somebody else.
Oh, what's her last name? Perry?
Perry.
It is Perry. I have a person named Perry Williams in my class.
Oh, how funny.
Yeah. But
Because she was struggling on her 107 the other day and I told her to jump on and ask for help, but she didn't.
yeah, what? Well, aren't you her mother?
I am her mother, but
Yeah, so why would she listen to you?
I know, exactly.
What were you thinking?
And I told her, I
just sent
said,
it, Doug.
Yeah.
I just sent it to you.
Oh, okay, thank you.
were you busy on Sunday?
Me?
Uh,
Oh, yeah.
Not busy. Like total is have 9 or 10 students, but they stay till the end. Like not busy, but
Yeah.
they're not leaving. They're not leave.
They're just hanging out so they have the
Yeah,
help
they
there
just-
right at their fingertips.
Asking question. I mean, same student ask question.
Yeah.
Not a ton, but the first Sunday is like 26 students that I have to call Doug to come help. But last Sunday is fine.
I know I had to call Doug last week too, on Monday.
Oh, I came in a
They were
lot. I need to write down. I was starting to write down every time I came in. Because
You came
I
in on
want-
Monday to help me.
I came in on another day too. Oh, on Friday, Bill needed to do something. His dog had medical problems. And so I covered Bill's 12 to 2 and I stayed till 3.
Oh, jeez.
So, yeah, I'm starting to I decided I would start keeping track of the extra time I'm putting in because it is pretty busy. And that's why, in order to justify having somebody come for more time.
Yeah.
Well, I'm going to try and get that. Thanks, Panyada, for sending me that. And I'm going to try and get that uploaded. So I have to leave to upload my.
Okay. All right. We'll see you later.
Thanks. See
Bye.
you.
Yeah.